Okay, so we are now going to continue where I left off yesterday, talking about some of these drug resistance strategies. Another strategy that we stopped at was the overproduction of the substrate or ligand for the target protein. So basically, the let's say you had an inhibitor that you were dosing a patient with. What, let's say, either the tumor or the bacteria, say, could do would be increase the amount of ligand that the cells produce for that enzyme that your inhibitor inhibits. Does that make sense? Or hopefully that makes sense. And by doing this, you're going to be using, again, Le Chatelier's principle to competitively block the ability of the drug to bind at the active site. You're changing the amount of one of the reactants in the drug active site in equilibrium, because there are two equilibria, remember, for the inhibitors, right? There's enzyme plus substrate, or there's enzyme plus inhibitor. Remember, there's two competing equilibria. So what you've done now is you've taken the S and you've added a lot more S into that equilibrium. And so now you have pushed that equilibrium, the enzyme plus substrate equilibrium, farther to the right. And that means there's less free enzyme available for the inhibitor to bind. So there can be less E plus I. So that's good. Cells are smart chemists. We've got to be careful. So an example of this actually in bacteria is back in the old days, in like the 50s, there used to be drugs called sulfa drugs. So they kind of came out after, after penicillin, and they were useful for a time, but bacteria figured out that they could overproduce p-amino benzoic acid as a ligand, and they could become resistant to the sulfa drugs, which sucks because they're pretty easy to make. Another thing that drugs do, that cells, be it tumor cells or bacteria, but typically tumor cells do, typically bacteria cells do. Strike that, reverse it. They have drug destroying mechanisms. And so, for example, the famous one of these is what's known as beta-lactamases. And so penicillin and all its related antibiotics have, as a key part of their pharmacophore, this particular lactam. So it's an amide bond, and it's in a four-membered ring. And it's connected to other ring systems. It depends on the particular antibiotic in the family that you're talking about, but they all have these beta-lactam structures. So that's it's called a beta-lactam. And what happened is that penicillin used to be this magic bullet. It was amazing antibiotic when it was first introduced back in say the 40s. When it was really getting widespread. It was just so helpful. And unfortunately, by 10 years later, because we didn't know anything really about antibiotics at that time, we weren't very good at it. We had already introduced resistance, in part because overuse, people not taking their full course, etc. And now, almost many different strains of bacteria. Here the example of Staph aureus, which is a common both disease-causing bacteria and a bacteria that lives on your skin, that lives on healthy skin. But when it gets into your body, it can cause a lot of different infections, typically cellulitis, or a lot of different other infections that can lead to life-threatening situations like cardiac inflammation, and etc. In any case, a very high percentage, I would say, of pathogenic bacteria are now resistant to beta-lactamase, or to beta-lactam, because they have this enzyme beta-lactamase. And one of the things that sucks about bacteria is that they can actually pass this resistance gene in between species. It's a rare occurrence, but once that gene has evolved, there is actually an interspecies, a method that related species can pass genes among themselves, and that meant that this plasmid evolution, or this evolution of resistance, only had to happen one time, and the bacteria are able to package it into the circular DNA called a plasmid and share with other species of bacteria. So it only had to happen one time for it to eventually get shared among a ton of other bacterial species. So this is another reason, A, we gotta be careful with how we use antibiotics, and B, we always need to be inventing more antibiotics. Okay, so another antibiotics are, another example of this are the aminoglycoside antibiotics. So some of these are kanamycin, which isn't used that much because it has kind of a low dose threshold for kidney toxicity, but it is used, and it's used in veterinary applications too. And neomycin, which is in your Neosporin preparations, among other things. It's one of the components of that. Bacteria can become resistant to these kind of enzymes these kind of drugs, because the way that these drugs work is they block RNA synthesis, they block protein synthesis by complexing with RNA. So they have these sugars that can complex. And so what bacteria does is that they can chemically modify their RNA to take out the H bonders in the RNA. So they're applying Lipinski's rules, and they got rid of some of these H bonding groups. And once the RNA can't form H bonds to these drugs, the antibiotics no longer work, because the whole idea was that these molecules stick to the RNA, and the RNA cannot be translated into protein. So another clever approach is actually to get around the resistance, was that they were modifying these drugs as well. The bacteria are modifying these drugs. And what they did was they made it so the bacteria couldn't modify the drugs. So you see here, they're able to convert it to a carbonyl, basically. Does that make sense? So here it's a carbonyl in equilibrium with the hydrate, and here it's an OH group. So they converted it. So this is in equilibrium. Okay. All right, so when a drug-destroying enzyme is produced, you want to make an analog to the new enzyme. So, for example, of kanamycins, if the bacteria is getting rid of that kanamycin, you take out the OH group. Right, so the bacteria is adding a phosphorate group here, so you remove that OH group, so it can't do that anymore. So that's kind of the more elegant. The second thing is to inhibit the new enzyme with a second compound. So what this slide is telling you is these are some medicinal chemistry approaches that we can use when we realize that there is drug resistance in a population, say that we're seeing drug resistant bacteria, for example. If we can figure out how that bacteria is drug resistant and realize that it's due to a drug destroying enzyme, then hopefully we can modify our initial antibiotic so that it's not a substrate for the drug destroying enzyme, but still works to kill the bacteria. So this is giving you the skills that you have to apply to do that, with the specific example of kanamycin to tobramycin. Okay, so something that cancer cells do a lot, is upregulate glutathione. And so glutathione is a really potent nucleophile, and this, it's not that your cells have it anyways. They have glutathione hanging around. It helps your cells control the redox environment in the cell. It's important to helping your cell do a lot of different chemistry and control disulfide bonds, etc. So your cell makes this anyway. So all it has to do is kind of upregulate how much it makes, and it can get rid of some of these electrophilic drugs, for example, those nitrogen mustards, which we said were really common anti-cancer drugs. And so I'll explain how that works in the supplementary slide on the next slide here.